All right. Well, good morning, everyone. My name is Andy Lyon, and I'm the Director of Conservation at the Kansas Department of Agriculture. I want to welcome everybody today to our breakout session on water quality. Just a few ground rules for our session here. Each presenter will have about 15 minutes to present and then about 5 minutes for questions. We will be monitoring the chat. So as you have those questions, please go ahead and type them into the chat, and we'll ask as many as we can with the time allowed. Again, you're in the session for water quality, and I really appreciate everybody joining us. When we look at the state of Kansas and we see 46 million acres in working lands, in working farms and ranches, we know that the management practices that are used on those working agricultural lands are really the dominant factor in our resulting water quality. And so we're really lucky today to be joined by three experts in the field of how land management impacts water quality. And so our first speaker today is Will Boyer. Will is an extension watershed specialist for K-State Research and Extension. He works primarily in Northeast Kansas with extension agents and RAPS coordinators, where they provide education and technical assistance to livestock producers looking for solutions to water quality concerns. Will's work has been focused on water quality associated with livestock for over 25 years. He has a bachelor's degree in biology from Chadron State and a master's in environmental planning and management from K-State. Will, thank you for joining us this morning. Please take it away.
All right. Thank you, Andy. Nice introduction there to comment about the working lands and their impact on water quality. That's a great comment. So you got a screen there now?
We've got you there, Will.
Trying to wake it up here a little bit. Get this out in case I need it. So, yeah, so I got the flashy idea of tale of two seasons. And the two seasons are one when it's super cold, and I got this all everybody's faces up here covering my screen, so I need to change that here. Give me just a second. All right, thanks. So when it's super cold, you got issues, and that's when the water quality issues related to livestock and the water quality impairment are the management of what's going on out there is really having an impact. The animals are often in confinement, and we have to bring feed to them. And if you want to provide an alternate water supply, you got to have a way to keep that water from freezing. Water is a critical piece to livestock production. It's the most important nutrient the animals have to consume. And then the other season is in the warm months when the ponds become drier and more stagnant, and we have flashy rains that might be bringing soluble phosphorus into the ponds. And these harmful algae blooms are so unpredictable. It's so hard to get your head around how they happen and what to do about them. And in terms of the best solution for a livestock producer is to just fence that pond out and don't let the animals have access to it. But there's so many cases where a pond is the only source of water in the pasture. So those are the two seasons. I just want to mention that getting started here that I'm a part of the RAPS program, and I'm a service provider to the RAPS areas in Northeast Kansas, and I help them with livestock projects. And something we've adopted across the state in the RAPS program is utilizing these cover crops as a forage source for the animals. And what that accomplishes is it helps get the cow-calf and the backgrounding operations out of the confinement pens, away from the water resources, and gives them a good quality forage to eat. And most importantly, it decreases the time they're in confinement and increases the natural distribution of the manure, as opposed to letting it build up in the confinement pens, where eventually the producer finds time to get that out onto the field with the manure spreader. So those are the big factors there. So moving on to trying to solve this problem of providing liquid water instead of solid phase water to the animals, because they can't do much with it when it turns hard. My first choice is if there's on a crop field, and the crop fields are kind of a particular challenge because may only be using, especially with the cover crops, we may only be using that field occasionally, and there's no fencing and no water development typically. So nearby there could be a pasture or a source of water that maybe from a well that's a pressurized system, like the pictures on the left. Or lots of times on an adjacent pasture might have a pond or a spring, and the top right picture shows a really nice gravity fed water system. There's a pond on the other side of that little dam there, and that water flows and it's buried. Most of the water is protected by the ground, and the sun maybe can shine on the water. You can turn a little valve on and trickle a little bit of water to keep that water from freezing up. The lower picture is a spring tank, and springs are outstanding resource for water in the wintertime. The water's warm and it keeps flowing, and you don't have this challenge of dealing with ice. So the next best choice that we'll look for near a crop field are often, there's often a farmstead access around a crop field. One that maybe is no longer a farmstead, but it's been abandoned, but there may be an old well there that can be utilized. And the great thing about the wells is that you can set it up so when you pump the water to the tank, the water can drain back down into the well that's in the water delivery line, and then that will keep that line from freezing. Then the next choice I'd pick to try to find a source of water for a crop field would be a pond. If there's a pond available nearby or within the field, you can set up a more expensive approach would be what we call a wet well, and I've got a graphic of that later. These pictures are all the freeze-proof hose pit and using an interval timer. The top pictures are this hose pit, which I've kind of invented the idea, I guess, of putting the water delivery line down in the pit and keeping it out of the cold weather, and then just a little horizontal or somewhat possibly downhill trench going out in the pond, and then the pump is out in the pond below the ice, and we can have the same kind of effect as a well. That water that's delivered from that pit there up to the drinking tank can drain back and then not freeze. The bottom pictures are showing actually a public water supply reservoir that the producer gets his winter time and sometimes summertime water from. And instead of giving them just sole access to the pond without another source, we tried out. And the pond was very shallow, and we tried, and we only needed to use it up until mid-December or so we didn't get into the super cold weather. But to keep it from freezing, we used a small centrifugal pump. Slid that out in the pond. You can see that little pump in my hands there. Slid that out in the pond and used an interval timer to turn the pump on periodically, and the water drained back from the hose in the tank back to the pond, and it just kind of, the water kept moving, and as long as the water's moving, it won't freeze. Then the next choice, none of those other sources of water are readily available near the site where you're trying to graze the cover crops, would be to use a creek, and then set a pump system up so you can pump out of the creek and into a nearby tank. You can do that with these frost-proof hose pits that I showed a little bit ago. And also another option is using a heat cable, which basically adjusts the temperature and the current that's drawn through that device based on what the temperature is that it's in. So I wrap these cables around a pipe, and then I insulate it really well, and then it helps keep the water from freezing right at the level of the water, and the pump will be floating out in the creek, and that so far has been working pretty well. And I'm going to put a couple more of those out in the next week or so, so we'll see how well that works this winter. Then the last choice would be hauling water, and that's a choice that a lot of people end up making. And compared to how expensive a water development can be, that may be the most economical choice. But the folks at the Watershed Management Section, KDHE, kind of challenged us to find some less expensive ways of doing that, and that's kind of what I'm presenting on here. These are usually powered by solar power when I'm helping somebody set one of these up. This site, you can see the tank in the distance. That turned out to be too far away from the pumping system and too flat. And we had some challenges. We had to actually, the water wasn't draining back enough when it got super cold, so we actually had to every day blow air back through the line to force it back into the hose pit. Here's an important piece that you can't just use any. Well, first you got to have a DC pump for the solar systems, and you need a pump that will let the water flow back. And these pumps have a centrifugal impeller. That picture kind of in the middle with the black background shows the impeller at the bottom. The picture just to the right of it shows multiple impellers that let you pump water from a deeper well. All the rest besides these two pumps here, all the rest of those pumps will only pump 10 to 15 feet high, or the one on the right will probably go more like 30 feet. But there's a limit to how far one of those single impellers pumps can pump, but the multi-stage pump with extra impellers gives it a lot more ability to pump. Timers have been a big piece in what I've been doing with folks on these. I mentioned the interval timer on the right, but also these daily timers. The other two pictures are two examples, and basically what I do with those is I find out how many gallons a minute the pump will pump, and then calculate how many hours or minutes during the day it needs to run in order to fill the tank so the animals have enough water. Set it so it'll turn on, like in this picture, it shows turning on at 9 and might run from 9 to 10. And then the animals drink the water back down halfway or two-thirds of the way to being empty. And then when fresh water comes the next day, then it's ready to drink. It's not frozen on the top part, so they can get all the water they need. At the bottom left is a picture of the wet well that I mentioned, and the great thing about that kind of a design is you can keep all the plumbing underneath the ground. Works really well adjacent to a pond, and it's definitely a preferred method of doing this, but it's not nearly as inexpensive as running over to the local recycling center and grabbing a stack of buckets and cutting the bottoms out of all of them, and having some strong and energetic water quality enthusiasts with you to do the hard labor of digging that pit and cutting that trench. So that's a project that we had a little help with, and really had a lot of fun that day. So you put those buckets down in that pit. You can kind of see this orange hose. There's the water hose comes out the bottom, and then it'll be placed out through this trench below frost all the time. And then there's a little bit of trenching work that's done out into the pond, and then the pump will sit out below the surface of the water quite a little in order to keep it from freezing up. And the intake of the pump is at the bottom of the pump. So that trench idea works all right. I tried something a little bit new at a different site near here. I also have a way of driving and washing a pipe over to the pit now that works pretty well, at least the first time I tried it. And then the other thing that I mentioned when you need to try to do this in a creek, and you have to deal with the fact that water levels change in the creek, not as much in the wintertime, but they do sometimes, is using those self-regulating heat cables. The picture on the left shows a PVC pipe that has another pipe within it, a heat cable around that, and then some extra insulation around the heat cable, all within that PVC pipe there. And then on the right, it shows the swimming noodle that helps regulate the elevation of the bucket, so that the water level of the creek and the position of that heat cable are in sync. So you're only heating a real small area and using a minimum amount of electricity, because they don't draw very much energy, but in the wintertime, you don't get a whole lot of energy from the sun. So making this work is you have to be a little conservative. So moving on to the hot summer season, and kind of a different perspective of water quality, something that livestock producers are I don't know if I'd say they're all particularly concerned about, but they're aware of harmful algae blooms and the toxins that come from those. These are two ponds that were within our Delaware RAPS priority area that I worked on this last summer. I've only been doing this sand filter thing this one summer, and it was led by Jody Holthouse, who was our extension livestock agent in that Meadowlark Extension District, but she's retired now, so it'll be interesting to see whether somebody can pick this up and carry on with it. So we're using slow sand filters to remove the toxins, and this was just a demonstration project to see if we could build one of these, or two of these actually, using materials that the typical farmer wouldn't be able to get their hands on. So we selected that mechanism based on watching a Zoom presentation, a conference focused on harmful algae blooms. And for public drinking water, the slow sand filter was really quite effective in not only keeping the bacteria or the cyanobacteria cells from getting down into the drinking water, but it also removed, when the bacteria cells die, they release the toxins, and it can remove the toxins as well. And the toxin removal, a lot of that happens in a biofilm that grows on top of the sand filter. This is some information that we used to kind of make our own design. There was this water research publication was specifically used to stop the toxins in the blue-green algae blooms, and treat those. And then slow sand filters have been used for home water systems and private water systems for a lot of years. Not so much in the United States, but in a lot of other countries that are very common. So there's the beginnings of our two sand filters. It's the food grade chemical totes. Well, producers use them to transport chemicals from field to field, and they can be used for a lot of other things, of course. We use a network of PVC pipes with some holes in the bottom and a discharge point up toward the top, just a little bit below the top of the sand level. Some gravel in the bottom, and the gravel we got was not clean gravel, so we washed it out and got all of most of the sediment and silt out of it before putting a layer of fabric over top of the gravel. The gravel you see on top of the fabric was just kind of there to hold it in place. And then we just used one grade of sand, And we tweaked the design. I didn't show that, but earlier on that design slide, it had multiple sizes of gravel and multiple sizes of sand, particle sizes. And we didn't feel that was a very practical way that, I mean, getting a producer to adopt something like this needs to be fairly simple and straightforward, or it's going to be too much of a burden for them to try to find 6 different types of material to put in the sand filter. So we limited it to 2 different sizes of material, and then the geotextile fabric in between the 2. As you fill the filter with sand, you gotta fill it with water as well at the same time to try to get the air pockets all filled and everything totally saturated. And we learned that just driving it down the road will help it all settle down and into place, and then be ready to go to work. I mentioned the biofilm, an important thing to make sure that you do to keep from damage of the biofilm with the inflow from the pump was to have a disperser. This is what little horse feeder that we use to turn into a disperser for our sand filter. You're only supposed to allow 2 inches of water on top of the biofilm to make sure that it gets the aeration and that it needs in order to do its job. So making sure that your filter was level was really important. So in this site, we just had to drive it up on a couple 2x6s to get everything level, and that worked out pretty well. You can see on the right up here's the little float mechanism we're using to turn the pump on and off. You could also siphon from a pond to a system like this, and that would really work pretty well and cut the costs down a lot. So that's something that a person might consider. This is a picture of the filter just a couple days ago. Just continuing to kind of look at it. Maybe going to try to look at its ability to stop E. coli as well. There's been studies that show that. We built them fairly inexpensively, and like I mentioned, if you didn't do the solar part and just did the siphoning, it'd be much less. And managing the biofilm, I think, is probably one of the biggest obstacles to getting this, in a readily usable format for the average producer to want to tackle. You have to, over time, the flow rate goes down, and you need to backwash or back flush the system and maybe skim some of the algae and film that's floating around to keep things flowing at the rate that you need. And it's a continuous flow, so you pump water in there and you just kind of have a day and night trickle coming into the drinking tank. So that's not optimal either, but it's relatively small. And one of these systems, one of the filters probably be enough to do 25 head and maybe up to 50 head if you manage it carefully. We actually did a little bit of water sampling. Man, it was expensive, and we had some help from a couple different funding sources for that. We only tested the water that was being pumped into the system 7 times, and there was blue-green algae present 6 times, and then those 7 times, of those 6 times, the algae level wasn't so high, and we only tested for the toxin 3 times. And the toxin actually made it through the filter 1 time, but it was at a low level, so hopefully that wasn't too bad of a result for our initial tests. And I actually wonder whether there wasn't a little human error involved in that one, because we didn't have a testing protocol or anything like that we were following. So anyway, that kind of wraps things up, some acknowledgements. Of course, the wraps program provides funding for me to work with livestock producers in Northeast Kansas. Jody was a great leader on the sand filter project. And then the bottom two, Center for Sustainable Ag and Alternative Crops, and then K-Care provided some funding for doing the water testing. Any questions?
Well, great job, Will. Due to time constraints, I think we're going to have to move on to our next speaker here this morning. I would encourage everybody to reach out to Will if you have questions, and you can certainly find somebody that has his email address. I would also highly encourage everybody. Will does a lot of field days, demonstrations. I would highly recommend that you get out there to one of their workshops and field days at K-State and RAPS. They often work in conjunction with our conservation districts to host those field days and see and get your hands on some of these techniques that Will's talking about. Great job, Will. We appreciate it.
Yeah, thank you, Andy.
So then moving on to our next speaker today, Dr. Nathan Nelson is a professor in the Kansas State University Department of Agronomy. He teaches graduate and undergraduate courses in soil fertility and nutrient management. His research program investigates nutrient cycling, fate, and transport in agroecosystems and develops best management practices that minimize nutrient loss and maximize nutrient use efficiency. Dr. Nelson is a Kansas native. He graduated from K-State with his BS in agronomy, and he received his master's and PhD degrees in soil science from North Carolina State University. Nathan, the floor is yours.
Thank you, Andy. I appreciate the introduction, and hopefully I'll target to end this just a little bit before 10:25, if that works okay. Okay.
That's perfect.
So I guess I'll say thanks to everybody who's joining us. This is excellent attendance for a virtual conference, and so I'm excited to have this opportunity to share with you a little bit of our research that we've been doing here on cover crop and phosphorus fertilizer management and their impacts on water quality. I want to thank my co-authors, Elliott Carver, Peter Tomlinson, Craig Rosenbaum, Gerard Klutenberg, and Deanne Presley for their assistance on this project. So we know that erosion and runoff from agricultural fields can cause problems both in the field, whether they're destroying the crop and removing nutrients, removing soil, things like that. They can also, this movement of soil and nutrients can also cause problems in our water, right? And so there are benefits to the producer and to the state in general if we're able to try and reduce erosion and keep our nutrients in the field and keep them out of the water. Once they're in the water, the sediment fills up waterways, can cause costly dredging operations. The nutrients when they're in the water, it's pretty much just about the same as when you put nutrients in the field, right? We fertilize our field, we get more crop growth. We fertilize the water, we get more algae growth, which can cause problems. Sometimes, we see here algal blooms in Centralia Lake and Milford Reservoir. There are some pretty big algal blooms that have caused major water quality concerns in Lake Erie, some others in Chesapeake Bay. They hit big headlines across the nation, cause political changes, but we also have things a lot closer to home, right? If you look here in Kansas, this map here shows the counties in the state that have had a harmful algal bloom identified by KDHE since 2010. And then those counties that are darker red, it counts the number of years. And so you see some of them nearly every year since 2010, we've seen harmful algal blooms pop up in these counties. Furthermore, we see that there are counties across the state. It's not just a local issue. It's across the state. We see counties where we've seen harmful algal blooms. And we see headlines like these here that we really don't want to see, people being warned about the safety of the water, about their opportunities for recreation, about other problems with the water. So we'd like to keep that those headlines out. And so the question is, and actually several years ago when we started the research that I'll be sharing with you, we had a lot of questions about cover crops, and would cover crops be a potential way to reduce phosphorus loss from agricultural fields? Also, could they reduce erosion? And we had good evidence that they would reduce erosion, but we already thought we were doing a pretty good job with no-till, right? And so now what if we put cover crops in a no-till system? Will they still reduce erosion? What water quality benefits do we get from this? So we had some ideas that they might reduce erosion, reduce runoff, reduce phosphorus loss, and particularly, we had a lot of producers that were asking about using cover crops to reduce phosphorus loss if they broadcast fertilizers. If you broadcast a fertilizer, it's faster, it's less expensive, and often this is done in the fall after other field operations are done, and you can apply your phosphorus fertilizer for next spring. However, from previous research that we've done here, we know that broadcasting fertilizer on the surface like this would have the greatest potential for loss. But people wanted to know, can cover crops help here? And when we looked around, we really couldn't find any data on it at all in the literature. And so we set out to answer some of these questions, right? So could cover crops reduce phosphorus loss from a surface broadcast fertilizer? How do they affect phosphorus loss from a subsurface placed fertilizer? How might these change the nutrient cycling in the system? How might it affect economics? So we had a variety of questions. And so we went ahead and put together what we call the Kansas Agricultural Watershed Field Laboratory, an outdoor laboratory where we have 18 small watersheds, each one about 1.2 acres in size. You can see them kind of checkerboarded across this hill slope here. And then each one of them has a single outlet where we can collect the water and monitor the water quality coming off these different experimental units. Here's an aerial view of that same field. We divided it up, like I said, into 18 areas. It's a terraced field, so the water comes down the slope, which would be top to bottom in this figure, and then hits the terrace and moves off. Each one of these triangles would be where it exits the field, right? And so in that area, we have 6 agricultural treatments, or 6 systems that we've been investigating, and then each one replicated 3 times. We started this in 2015. That was kind of a work-in year where we're working into a cover crop and a no-till system. So I'm going to be presenting data from 2016 through 2019. It's a corn-soybean rotation. Our treatments were 3 different phosphorus fertilizer treatments, either no phosphorus fertilizer applied at all, or else about 55 pounds of P2O5 applied as a fall broadcast, or the same rate applied as a spring injected in a 2x2 placement. And then those 3 phosphorus treatments are all present either with a cover crop or without a cover crop. And the cover crop varied throughout the study. Really, it's the winter wheat or triticale, the small grain that really persisted through the winter. But often we had rapeseed with that, and then in one year we had hairy vetch. But really it was that winter wheat or triticale that really persisted and was the main, produced most of the biomass by far. So like I said, at each one of the outlets, we had an H-flume and we had some water sampling equipment. So we collected runoff from every single, we collected water samples from every single runoff event. We measured the amount of runoff that came off, determined sediment, total phosphorus, and dissolved phosphorus concentrations in the runoff. We also looked at a lot of agronomic and economic measures. I'm not going to be talking about those today, but if you have questions, I'm more than happy to answer them. Let me talk just a little bit about the rainfall during these years. You can see the blue dotted line, that's our average precipitation pattern through a water year from October 1 to September 30th. And then the 4 different years we had 2 years, 2016 and 2019, they're above average. 2 years, 17 and 18, they're below average. One that was a really dry year, one that's really wet year. In the end, we had a lot of variability that became average if you put all 4 years together, right? But understanding these differences will help us understand some of the patterns that we see variability from one year to the next. So remember, we got some wet and dry years there, really wet and really dry. If we look overall on runoff, that was one of the first things we wanted to look at is how does it affect runoff? And we really found that there wasn't much impact of the cover crop on the total volume of runoff from the experiment. I just got a message that says that the breakout room is going to close in 50 seconds. Is this correct, Andy?
Not to my knowledge, Nathan. Please keep going, and I will try to figure out what's going on there.
Okay. In my experience with Zoom, I will have no choice. We will all get booted out of this in 36 seconds.
Yeah, I'm with you. Let me see if we can do something to try and stop that.
Okay. Well, I've got 27 seconds to go through this slide, see if I can do it. So we didn't see that the cover crop really reduced our runoff at all, but what it did do is it reduced the peak flow by quite a bit, about 27% lower peak flow. So we had runoff coming off a lot slower, a lot, or not as, the peak flow was quite a bit less. Then
picking up real well. So again, Nathan, apologize for that. Please go ahead and pick right up where you left off.
Okay, no problem. I'll have to say that everybody was pretty quick to get out and get back in, I guess, because
Absolutely.
We're almost back to everybody back in here. I think we had about 113 to begin with, and now we're at 104. So few stragglers that might still join us, but or maybe they'll opt for a different room. Anyway, so I'll pick back up here where I was kind of talking about runoff intensity. And so what we see is happening here is the cover crop slows down the time to the initiation of runoff. So adds about 5 minutes before we get runoff initiated. Then it adds about 7 minutes to the time to peak runoff, right? So it takes a little bit longer to get to the peak. So it's stretching out this, and then adds about 45 minutes to the duration of runoff. Andy, I've got this.
I see it again, Nathan, and I think they're having some technical difficulties. Please keep going, and if we get kicked out again, we'll do the same and just have everybody try to please join back into the water quality session as quickly as possible.
Sure, yeah. I don't know how. I don't know what to recommend here, but so in the end, what we see is the runoff. Although we're not affecting the overall runoff by a whole lot, what we are doing is changing the way it's slowing down that runoff, right? Whoops, let me go to the next slide here. So if we look at the runoff over the 4 years, we see, again, 3 of the 4 years we had no effect on overall runoff. In 2019, that was our wettest year. And in that year, we did have an impact where the cover crop reduced rainfall. Did we have that effect on runoff? What we did see, and this figure here on the right kind of shows 2 hydrographs for a single event, one with a cover crop, one without. And you can see that the one with the cover crop has a lower peak. The peak occurs later. The runoff occurs for longer. Those 2 hydrographs actually have the exact same amount of runoff. It's just a different pattern, right, of runoff. So with the lower intensity of runoff, we saw quite a bit less erosion, even with no-till. Some of these erosion rates for a few of these years are pretty low. If you look at that, you've got even 1,000 pounds, that's half a ton per acre, which is often thought of as a pretty decent decently low rate, but we decreased it even more, right? 60 to 70% decrease. In that 1 year where we had that wettest year, 2019, we had about 2 tons per acre of erosion, whereas dropped it down to half a ton. Gosh, I'll keep going, Andy.
Please do.
You can see in the photo on the slide that we have, the difference. You can clearly see a difference in the turbidity of the water coming off the field. So the cover crops are doing a great job at reducing total sediment loss, but generally we would think that they would reduce total phosphorus concentration as well in that water. But we did not see this happen on a regular basis. So in 2 years, we saw no difference. In 2018, we actually saw total phosphorus concentration go up, and then in 2019, it drops again. So a highly variable effect. 2018 was our driest year. That's when we saw total phosphorus concentration increase with the cover crop. 2019 was the wettest year. That's where we saw total.
We've got just about everybody back in, and I know, folks, this has been difficult, but please try to focus on this part, Nathan. This is very important stuff. Please go ahead and proceed, sir.
Sure, no problem. So, anyway, we, in the really wet year where we had, we reduced erosion by about a ton and a half, right? We saw a decrease in water quality, or a decrease in total phosphorus. The other years, even though we were decreasing sediment loss, we were not decreasing total phosphorus loss. If we look at dissolved phosphorus concentration, we're actually increasing it. So the concentration consistently increased each year, on average about a 70% increase. Even in 2019, where we had that wettest year, we still increased our dissolved reactive phosphorus concentration in the runoff. These are concentrations. The concentrations tend to drive our loads. The first 2 years, we had no difference in runoff. 2018, remember, or first 3 years, sorry, no difference in runoff. So it's really that difference in concentration that drives the difference in load. In 2019, we had an effect on runoff. So here we're seeing the actual mass of phosphorus loss. We can see somewhere between 1 to up to 8 pounds of P2O5 per acre was lost each year. And again, 2 years, 2018 and 2 years, 2016 and 2017, no effect on total loss. 2018, an increase in total phosphorus loss. 2019, a decrease in total phosphorus loss. The important thing here is to note that we're still increasing dissolved reactive phosphorus or having no impact on it. And dissolved reactive phosphorus is more bioavailable. So it's possible that, well, that's not a good thing to see that increase, right? We'd like to see total phosphorus and dissolved phosphorus both decrease. Now, so this has been focused on the cover crop effects, right? Well, we have these phosphorus fertilizer treatments out there as well. So let's look at how the phosphorus fertilizer treatments affected runoff concentrations. And I'm going to jump straight into our phosphorus loss. That's where these fertilizer treatments had their biggest impact. We see that consistently, so here we're looking at concentrations again, concentrations of dissolved reactive phosphorus and concentrations of total phosphorus. And consistently, we see that the concentration of dissolved reactive phosphorus decreased when we injected with that spring injected treatment. So the concentrations consistently decreased with spring injected fertilizer application. We did still increase our concentrations over the control with spring injected, but we're adding more fertilizer, right? We're adding phosphorus and maintaining a higher soil test phosphorus concentration. If you look at total phosphorus, we see that We decreased total phosphorus by spring injecting that fertilizer into total phosphorus concentration in 2 of the 4 years. The other 2 years, there was a tendency to decrease it, but just wasn't quite significant. In 2018, a lot of that is actually due to the fact that we had a drought, and so most of our runoff occurred either before our fall applied fertilizer or well after all of the fertilizer had been applied. Again, if we look at effects on loads, fairly similar. We see the concentrations are really driving our loads. We see that dissolved reactive phosphorus decreased by about 5% up to 50% by using the spring injected. So the fertilizer management is a pretty good tool to decrease our phosphorus fertilizer, our phosphorus losses, right? And tended to do a pretty good job of decreasing it most every year. The 1 year where our dissolved reactive phosphorus didn't decrease, that was that really dry year where there really just wasn't any runoff during the growing season. It was all before or after we had applied the fertilizer. So in summary, our cover crop did an excellent job at reducing runoff intensity, although it didn't reduce the volume as consistently as what we had thought. It decreased total phosphorus loss when erosion was high, but when we had lower erosion events, it had no effect on total phosphorus, or it increased it, and consistently increased dissolved phosphorus concentrations. Our spring injected fertilizer treatment consistently decreased our dissolved reactive phosphorus concentration. And so what I look at here from a general recommendation is that cover crops do a good job at reducing sediment and protecting our soils against erosion. I think they're a good conservation tool for that. But sediment, we also have phosphorus loss problems here in the state, or we want to reduce phosphorus loss from our fields to protect our water against that. And in order to protect against phosphorus pollution, we need to use fertilizer management, good practices with our fertilizers. We want to subsurface place the fertilizer to reduce that dissolved reactive phosphorus loss from the field. I will say, I'll put this link in the, this study's been published here. This is the citation for the study. I'll put that in the chat so that those of you can click on that. And actually it's you can download that article for free. We wanted to make sure it was available we knew there were a lot of people here in the state with state agencies and so forth that might be interested in this and wouldn't have subscriptions to the journal. So you can download that for free. I want to thank our team. We had a lot of students, a lot of undergraduate students and research assistants that have been working on this project and are continuing to work on our second phase of this project. I want to acknowledge all of them and thank our funding sources, the 4R Research Fund, the Natural Resource Conservation Service, the Soybean Commission, the Corn Commission, Foundation for Food and Agricultural Research, and U.S. Department of Agriculture. With that, I don't know if I have time for questions.
Yeah, Nathan, we're gonna try real quick to just look at 1 or 2 questions. You know, I would say that the important thing in my mind is that your research is confirming that conservation systems and not individual conservation practices are really what we need to be focusing on. So again, I think this is vital research in our outreach and our program development. So we did have a question. One, do you think there would be any difference in this research using different cover crop mixes?
Sure. So that's a great question. And I think it might go into the next question that I noticed is why we might be seeing increased dissolved reactive phosphorus, right? So Elliott Carver, the graduate student on this study, has done some other work looking at phosphorus release from cover crop tissue. And just recently finished a field study looking at the release over time and the cover crop residue decomposition, mainly for different small grains. So looked at winter wheat, barley, oats, rye, and some mix of those. And mainly oats tended to have a higher, tended to release more dissolved reactive phosphorus than the others. The others seem to be a little bit more similar. So I don't think that we would have seen drastic differences if we had have changed that small grain. Now, if we had have looked at other cover crops, maybe, but the problem is they just don't last over winter. It's really the small grain that persists over winter. And so, and we are, I guess, just to give you an update, we just finished the second year of our, another study started in 2020. So we just finished our second year of that. That study, we've been using cereal rye, and in general, we're seeing similar results there as far as the cover crop effect on dissolved reactive phosphorus.
Well, thank you, Nate. This has been a great presentation. Again, I apologize for the interruptions, but you did a great job. This is just vital research for us to understand how these practices play in together. So again, thank you very much.
Thanks. And I'll try, if people have questions, I'll try and answer them in the chat as we go on. Okay.
Appreciate that. So we're going to move on to our final speaker here in this session, and I can't guarantee that we're not going to have some more of the problems, but we are going to turn it over to Travis Sieve. Travis is the section chief of the Watershed Management section at KDHE. He leads the RAPS program. Travis, I'm going to cut down on your intro. I'm going to turn it over to you and let you get going.
All right, can you see my screen, Andy? Can you hear me?
We can see it. We can hear you.
All right, guys, I'm gonna maybe go the little faster than I expected to on this one because I don't know whether we're gonna get kicked out here in about 6 minutes. So again, I'm Travis Sieve with Watershed Management section here at KDHE, in which we are tasked with running our water quality program to meet the water quality standards in our surface waters in Kansas here. RAPS, I hope many of you have heard of this before, our Watershed Restoration and Protection Strategy. Really is a framework that we use. It's not only a program that's based out of the Clean Water Act Section 319 program, but RAPS is more of a process of collectively bringing partners together, whether those are local stakeholders, producers, agencies, both federal and state, bringing everybody together to develop strategies and plans to approach our water quality problems. This state's very unique depending on which region you're in. And so we realize to be successful, these locally led projects need to be worked through this process of assessing our water quality problems, planning on the best strategies to focus those, and then implementing. We have a lot of public land or private land here in Kansas. And so our strategies rely mostly on volunteer actions from those producers. Just quick map here. I'll kind of skip this a little bit, just kind of showing you the coverage of where we have plans built for the state of Kansas in regards to water quality on surface water. Really what I want to talk today about is some innovative things that we're doing and with the RAPS projects and the process here of always looking for more tools in the toolbox. Andy's going to recognize a few things out here today, you know, from his years with us. You know, the concept of building a toolbox to have the right tools in each watershed to implement these practices on a volunteer. And as you can see, we're more than just a cost share program, but cost share is a tool that we can use for financial incentives there. Information education, outreach, partnerships are a very large aspect of our toolbox. And then building relationships. We're going to talk today about a little bit of the innovative things that we're building tools into the RAPS toolbox moving forward. Soil health has been probably one of our big strategies, which we're building tools around. I think, you know, Dr. Nelson's research shown us a lot of good things that we're really wanting to look forward to. And how do we put tools with those to move forward with getting the adoption of soil health? I think when it comes to soil health, there's a few things. When we look at it from water quality to keep in mind, and again, I think Dr. Nelson hit this really well, it's the system itself. There's not just one practice necessarily that's going to make soil health improve to see our water quality benefits, but it's more of taking the system as a whole and trying to implement practices that build soil health in different ways and to help with that. Soil health principles cover everything from just not disturbing the soil to making sure residue is on there to armor that, provide diversity, keep a living root in the soil, integrate animals, and then knowing the context of your rotations, what you're trying to achieve. Context coming from the Soil Health Academy and understanding ag, I think is a vital principle when we're looking at soil health. What are we actually trying to achieve? What are we trying to achieve it in? So looking at your rotation, the economics of the producer to achieve these improvements all need to be coming into that. When we look at non-point source pollution, what excites me about soil health is non-point source pollution really is a symptom of a bigger problem for us. The problem that we're seeing here is actually the function of the watershed, the hydrology of the watershed. When we have watersheds that have increased amount of runoff and increased velocity of runoff is where we see our problems, excluding some kind of quasi, point source, non-point source problems where we have livestock setting in the stream, which is a little bit different. But when we look at general agriculture, cropland production, it's how the water reacts through the watershed is really what our problem is. So when we have reduced infiltration, that increases the amount of runoff that we do have and the velocity of runoff with improper soil health. Fertilizer, sediment, chemicals, they all inherently move with that water across the watershed and across those fields and landscapes, ended up in our surface waters here. So when we look at soil health, we're really looking at the function of the soil, gives us the function of the watershed in a direct comparison to water quality. So our goal is to decrease the amount of runoff over time, to increase that infiltration, have less water moving across that surface. Realizing this is a longer term goal. We work with a lot of producers who don't quite see that, and I think the research shows that too. That's not one of the first things we see is that increased runoff. Long term, what we're hoping for is to see more water actually go in through and properly function through the hydrologic cycle of that watershed by infiltrating. We do see a lack of runoff though. When we do see that lack of runoff, we do see lack of moving of substances. Those fertilizers, chemicals, sediment, bacteria, less runoff will decrease the amount of contaminants that it's taking as well. One thing the research is definitely already starting to show, and what we see a lot of our producers see, is that decrease in the velocity of that water moving across. And that's really about covering that surface and building that armor, building some resistance on that surface. So when the water that does not infiltrate is moving across, we're slowing it down. As the research just showed from Dr. Nelson, we are seeing sediment decreases from that. Speed of water being slowed down. So seeing that improvement coming there is probably one of our quicker. And then wanting to see decrease in inputs over time. A lot of the producers we work with are decreasing the amount of fertilizers and chemicals that they're placing on their field as they see their soil health improve. I think this really shows that nutrient management needs to be part of not only how we take care of our soils, but when we do have inputs, nutrient management plays a very vital role in where we see soil health and water quality. Go over this real quick. Andy, you definitely recognize this one. This idea, as we all like to say, ecosystem restoration, that through soil health, through improving the function of the watershed, we see the actual ecosystem restoration. Obviously, we're talking about water quality, kind of in this cycle, this breakout room right now, but looking at farmer resilience, rural development, water quantity, wildlife habitat, flood mitigation, drought resiliency, all of this really allows us to see the benefits of soil health. So where we don't necessarily see everything through water quality that we want at first, we might see aspects as far as drought mitigation get a little better, or farmer profitability seen a little better, nutrient density, wildlife habitat. So we're looking to improve all of these functions together. Once every one of these smaller circles starts to improve, more likely we're seeing other of these smaller circles improve with that as well, with soil health kind of being that strategy. So back kind of to our toolbox there of, ways that we're wanting to increase the adoption of soil health in Kansas. The toolbox right now for RAPS is set up with all the traditional approaches that we do. Our cost share incentives, whether that's to get someone to, move to no-till, to do nutrient management, to try cover crops, to plant a field border, a buffer around their field. That traditional cost share exists still for us and still a viable tool. As we see with soil health, though, information education is increasing, that we're needing to keep that as a tool in the toolbox. And then partnering with agencies and organizations, whether that be with the local conservation districts, with NRCS, FSA, Forest Service, Parks and Wildlife. We want to keep these, these partner agencies in the toolbox as well, of us all working. As that last slide showed, we're all going to benefit from the increase in soil health in one way or another. And so we want to work together to make sure that we're, having the same push. Where we're really looking at with RAPS, though, is to build new tools as we approach. And soil health has given us, a complex problem already on top of non-point source being a complex problem. How do we get people to voluntarily change the way they manage their agriculture business? One thing that we did notice is that infrastructure needs are needed to be there. Equipment. Some of these soil health principles do require additional equipment or more efficient equipment to fulfill increases in soil health. Traditional agriculture in some cases require different equipment there. What we see with the equipment is it's the majority of the time too expensive for one individual farmer to go out and buy all the equipment they need. But on the other side, we do see that increased equipment availability and types of equipment can aid us in our large scale implementation. We are trying to make large scale. This is greater than just field level. We're trying to affect the entire watershed as a whole. And so there's quite a bit of acres out there that we need to affect. And so new equipment can help us achieve those large scale implementation goals. As you can see here, there's a picture of an interseeder, which KDHE worked with the city of Wetmore and Glacial Hills RC&D to facilitate buying interseeders to have up in our northeast area, primarily some in the central area, of having interseeders go through that can interseed cover crops into our fields. And so this type of equipment with a 120-foot boom can more efficiently put on cover crops in a more timely manner. This also allows producers to have these cover crops placed in before harvest. And so for timing, when that becomes an issue, it allows us. Now, the way we're working with these interseeders they're a partnership with ag service providers, in which we work with those ag service providers to provide the service of utilizing this. These are about $500,000 per pop. Again, we're not expecting a lot of producers to be able to go out and buy their own interseeder, each one of these. And so what we're trying to do is build a tool where equipment is in the right place. We also have some roller crimpers in some areas for the termination of cover crops, where a lot of producers are seeing the benefit of that residue staying on their field versus harvesting it or even chemically killing it. That this idea of crimper rolling is a little bit better option for them. Weed suppression being one of the main things. And so we're getting roller crimpers out in that area as well. Some of the problems that we run into, though, with building this infrastructure around equipment are, one is the funds. Even from an agency standpoint, it can be fairly expensive. But then the other aspect is everybody needs the equipment at the same time. And so we're still working with our partners and stuff to say, how do we best get this equipment that can be used? Working with our ag providers, we are now starting to look at small service providers that do custom plantings to help us to start build businesses around a service providers for this kind of equipment that everybody needs at the same time. Technical services are another tool that we realize that we need to get into the toolbox here. Our basic understanding of how we do information education usually revolves around workshops, and it's a very good approach, but realizing that workshop just needs to be one tool, we need other tools for this, for technical services. So we've partnered with a few different groups. Understanding Ag is an excellent group in which we do have Shane New, which is a Kansas citizen, is part of that organization that works all over the nation and internationally in some cases now to consult on soil health implementation. And so they work as a consulting firm to help people not only understand as a community the importance of soil health, but then to work with individual producers to help them build up their own system. Through that, a connection with them is the Soil Health Academy, in which we do host larger workshops And they're more than just workshops. They're really, highly sought out educational workshops when we work with the Soil Health Academy. Bringing in experts from the local area and really diving into the principles, why they matter, and how to implement those on your property. I hope many of you have heard over the last few years, or the last year here, of the farmer to farmer work that we're doing. This is a kind of a multi-pronged approach that we're working on, but the idea is to have peer mentoring and coaching by experienced farmers. So farmers, over and over again, we see that they trust their neighbors as an information source a lot more than they do a lot of other places. So in finding those soil health champions within a certain area, what we're wanting to do is to have them go out and do one-on-one mentoring with their neighbors. We piloted this in Western Kansas. A couple of our experienced producers, Bryce Custard and Michael Thompson, have both helped us start to kind of figure out how this pilot works early last year. And we also applied for an EPA grant from the Gulf Coast area to facilitate a farmer to farmer coaching program on the eastern side of Kansas here. And we're just getting that started this fall, going into winter. Most of the areas where we got our coaches identified, and we're working on getting the infrastructure built on that program. The idea behind that is that we build farmer to farmer networks where farmers are being coached today by experienced producers in soil health, and they will become the coaches for tomorrow. And they'll start to actually build a network in their community based on the soil health needs and functions within that networking group. What works in Western Kansas doesn't always work in Eastern Kansas. And so we need to know a lot more locally driven coaching going on. We just received also a NIFWIF, the National Fish and Wildlife Foundation grant, to help with the farmer to farmer idea of when farmers are being coached, when they're ready to move on to actually implementing these practices, is to help them navigate state, local, and federal programs, specifically the Farm Bill programs, of how to utilize those programs to implement those soil health practices that they're being coached on. Another aspect of a tool for technical services we've helped facilitate with General Mills is the Kansas Soil Health Alliance. And this really is a farmer-led effort. I think all of our agencies are doing a great job of leading and building our programs to more facilitate the increase in soil health. But what Kansas was lacking was really a producer-led group here, for them to help us format our programs, for them to help push the networking and the coaching and the education push for each other as a peer network. And so the Kansas Soil Health Alliance was created last year. And I would recommend everybody who's interested in soil health to have that kind of be your number one spot that you look at for information. They work with all the agencies involved to run a calendar based off all the events to make sure there's a one-stop shop to find out where soil health events are going on. But then are working with the agencies to make sure that our programs are based in reality of what producers need and want, and helping us kind of design those. Am I still doing good on time, Andy? Oh, 60 seconds.
You got a minute left.
All right, guys, I apologize for how fast I'm talking on. The other aspect of this is bringing in new partners. The Ecosystem Services Market Consortium, which, as you see there, is a lot of producers there, are bringing in industries that are looking at buying both inset and offset carbon credits. And so we're working with them, realizing that as they produce their carbon credits, we are receiving our water quality benefits from that as well. I know carbon credits are kind of a hard subject to talk about right now. There's a lot of different groups looking at those. But from our evaluation, working with these groups, we're looking anywhere from $10 to $40 per acre based on carbon that they can sell, their carbon on the open carbon market, which gives them the ability to not rely only on commodity prices and allows them to take the risk of implementing soil health with having other aspects they can sell. I mentioned the agriculture service providers with the equipment. Municipalities